today's speaker is Tristan McLoughlin, whose institution I think I got wrong on the list, didn't I?
Yeah,
Today, so.
I moved recently.
Okay. To talk about testing the AdS CFT S matrix.
Okay, well, thanks for the opportunity to talk. And so this is my title. Yes, I'm now at Max Planck in Gulm, Potsdam. Okay, that worked? Yes. Okay, so there's been obviously a lot of progress recently in studying long operators in the context of AdS CFT, which are dual to classical strings, and calculating their anomalous dimensions. And obviously, a lot of this progress has recently, been possible because of the presence of integrability in the problem. There's, classical integrability on the world sheet. There's good evidence, as we saw yesterday, that there's quantum integrability. And in the dual gauge theory, there's very strong hints that there's at least perturbative integrability. So they're order by order that there's integrability in sort of the spin chain description, in looking at the dilatation operator as a Hamiltonian for a spin chain. And integrability, it's obviously a very well-developed subject. It's very powerful tools. And in particular, the beta ansatz allows us to sort of diagonalize the Hamiltonian and all the higher charges sort of simultaneously and extract numbers and solve the difficult combinatorial problem. Actually determining the S matrix that we want to feed into the beta ansatz is, of course, sort of the key thing that we would like to do. And there's been a real, like in the last year or two, there's been a tremendous progress in actually finding what the S matrix should be, for at least for the asymptotic regime, for the long operators, to find the exact S matrix to all orders in the AdS coupling. And this was a series of works, starting off with AFS and moving through BDS, Hernandez-Lopez, and so on. And then recently it's culminated in this work of Beissert, Hernandez-Lopez, and Beissert, Eden-Staudacher, where they gave a conjecture for the exact S matrix. Now, you can't prove yet, we can't derive this S matrix, we don't know exactly how to calculate it. So therefore, but it's passed a number of very rigorous tests, and so we have confidence that it's at least capturing a good portion of the full answer. We'd like to have a sort of a direct way to calculate it, and that's what I'd like to do today. I'd like to sort of present two perturbative approaches for calculating this S matrix. It's sort of like an old Woody Allen joke. I'd like to give a clear, conceptual, interesting talk, but I can't. So I'm going to give two, technical, boring, but hard calculations instead. I'll try and not, kill the entire speed by, sticking on the details for too long, but that is what I'm going to try and do. I'm going to do two kind of perturbative calculations to test this S matrix. It's based on work. So the first part, the weak coupling gauge theory perturbation calculation, is based on work with Beissert and Royban. And the strong coupling sigma model calculation is based on work with Close, Minahan, and Zarembo, which Thomas gave us some introduction to yesterday very nicely. Okay. So, oops, I seem to be having issues. What is it? Okay, whatever. It seems to be working. Okay, so I've said this is the outline that I'd like to discuss. And specifically, I'll give a sort of a brief introduction. I guess I was overly negative. At least at the beginning, I get to talk about the interesting ideas that people have introduced recently. And these are very powerful conceptual ideas for studying this problem. So as I said, particularly I want to study this conjectured S matrix. And the first thing I want to do is I want to sort of cast the S matrix and show what the sort of perturbative spin chain Hamiltonian corresponding to this exact S matrix is, at least sort of perturbatively. And I'm going to be most interested in sort of the for-loop expansion. And then I'm going to match this sort of spin chain Hamiltonian with a direct calculation from the gauge theory. Now, doing a for-loop gauge theory calculation is, of course, just monstrous undertaking. What we'll see, though, is that in this case, we really get very lucky. There's, using the symmetries and known results, you can do this calculation, well, with the right collaborators, you can do this calculation in a very short period of time. The methods that we use, though, in doing this, so this actually provides a very nice check of certain sort of aspects of the S matrix that initially don't look like they're sort of natural. The actual methods that go into it, though, it's not clear that they sort of generalize naturally to sort of more complicated problems that you would like to discuss. The second part that I'll do then is I'll discuss this near flat space model. This is an approach to studying sort of a simplified limit of the string sigma model. where we can actually do explicit calculations at strong coupling. And here, I'll discuss a two-loop calculation so that we can match the S matrix at two loops. And indeed, we'll see that it will actually agree. The thing about this model, though, is actually it's quite nice. It really does capture an awful lot of non-trivial physics about this problem. And it's a simplified truncation. And there's a lot of questions, and I'll try and discuss a little bit about them. But I just want to, as I'm going through it, I want to discuss like several things that it kind of does capture that you might think it might miss. For example, the symmetries of the model are very closely related to the symmetries of the full problem, and indeed it sort of captures nearly all of sort of the non-locality. One of the things about the sigma model and light cone gauge is that the model has this sort of world-sheet non-locality, which gives rise to these interesting properties such as non-trivial braiding, and this near flat space model has this too. You can describe a universal R matrix. You can do a lot of the same techniques that are useful in the full problem. You can do it in this simplified model. And similarly, it also has Magnon solutions and so on. And I'll briefly just run over these because, as I said, I think this model is interesting. So this is sort of like a little advertisement. And then I will describe the higher loop calculation, as I said, to two loops in large Tufts coupling, and we'll see that it does match with the conjectured exact S matrix. Okay. So just to kind of quickly set the stage, I'm sure this is all reasonably familiar to everybody, we're looking at the n=4 super Yang-Mills spin chain. And obviously a lot of the progress has moved from, instead of considering sort of like correlators, to considering like a matrix problem, where we sort of consider the dilatation operator, so the eigenvalue problem for the dilatation operator, and it can be mapped to a spin chain problem, and this of course then led to the introduction of all these tools that have made solving the problem so possible. So as the kind of simplest example is the SU2 sector, where we just consider two scalars, two complex scalars in the full theory, and we look at single trace long operators. This is the sort of the regime that we're going to be interested in. And the one loop dilatation operator is just the Heisenberg spin chain, right? This was the sort of first thing where people went, well, this is sort of, shows that the Heisenberg spin chain is almost like the simplest or one of the quintessential examples of an integrable model. Okay, the SU2 sector, which I am going to focus on, at least in the beginning, it's perhaps not the most physically relevant sector. It doesn't. You might think you want to go to the SL2 sector, where you sort of seems to be more related to cusp anomalous dimensions or scattering or so on. This sector doesn't capture those physics that we would like to maybe be most interested in. However, technically it is sort of the simplest closed sector, and so it's very useful for performing sort of explicit checks of the conjectures, and that's why I will focus on it. The Hamiltonians, this is the one-loop Hamiltonian. As you go to higher orders, of course, the Hamiltonian becomes long-range, with the order of interactions being the same as the loop order. And as I said, there's sort of evidence for higher loop integrability just using perturbative calculations, and there's, of course, an all-loop integrability from the dual sigma model. As part of the construction of the Hamiltonian of four loops, we'll actually explicitly see that the four-loop Hamiltonian has to be integrable. It essentially just arises from the symmetries. So we have a Hamiltonian, or we have a spin chain, so we want to define a vacuum state. So we just consider sort of an infinitely long chain of a single type of complex scalar fields. So this is a protected state. And as I said, we are interested in the infinitely long asymptotic regime. This is sort of the main restriction of a lot of the work these days, is that we always have to go to sort of long states. We can't look at short states. Now we can look at sort of single impurity states, where a single magnon insertion. And this can be calculated to all orders in perturbation theory. It was done by Gross, Mikhailov, and Royband in 2002, and others. But the reason I want to, in some sense, this result, the single magnon dispersion relation, almost follows just from symmetries, or you can get it from superspace arguments. But I want to go through a little bit about how they actually did this calculation, because it picks out sort of the simplicity, the trick that allows us to do the four-loop S matrix calculation. Okay, so we consider sort of single trace operators here, although I've kind of pulled off the trace part because we're in the sort of asymptotic regime. We don't do the sort of look at this particular linear combination. As a normal thing, we have some sort of vector space of operators. We want to renormalize them, and we want to calculate this renormalization parameter z. And then from this, we can just extract what the anomalous dimension or the matrix element of the dilatation operator is. In this case, it will just be given by the leading pole in epsilon, so we'll work in dimensional regularization. in all these cases to regularize our UV divergences, and then to calculate the matrix elements, we just want to pull off the leading pole. Now, as I said, here they were actually able to do this calculation to calculate the sort of one magnon dispersion relation to all orders because the interactions that they need to look at were so-called maximally shuffling, and this is the trick. For these types of interactions, and I'll show examples, all the interactions are simply just permutations, right? So here you have a phi, it switches with a z, it switches with another z. So all interactions are just permutations of operators. There's no exchange of identical particles. And so in this case, you never switch a z with a z or a phi with a phi. In this case, it's sort of kind of reasonably clear. But this again simplifies things remarkably. And also at L loops, the interaction involves L plus one sites. So here's sort of the relevant diagram that they need to evaluate. And as you can see, so I have this red line corresponds to my magnon, my impurity, and it just scatters against L sort of vacuum sites. This diagram is just a chain of bubbles, right? So you can sort of evaluate down here. I have this sort of little triangle. Of course, this line is sort of the operator insertion, right? So this is the operator I'm trying to calculate the anomalous dimension to. So this is really just like a sort of a single point. So this is just a bubble. So I can evaluate bubbles exactly, right? They're just given by this expression here. Here I've actually evaluated the bubble for arbitrary powers of the propagator. So you're going to see a bunch of diagrams like this. So here I have a propagator which is coming with some power a1, and I can evaluate these things explicitly. They're given by this sort of standard formula. But if you integrate this bubble, you just get a sort of another propagator, which gives you a bubble, which gives you a bubble, which gives you a bubble, and so on. So you just get a chain of bubbles. And so this diagram, as I said, just becomes a chain of bubbles, although the powers of the propagators pick up these infinitesimal parts, these epsilon parts. Okay. So you can resum all of these diagrams, and then you can extract what the anomalous dimension is. There is a couple of assumptions which actually go into this calculation. They do have to assume sort of a smoothness in sort of the infinite limit, and they do have to sort of assume that the momentum sort of appears in certain combinations, and they explicitly checked this at low orders. It's not so relevant to my point, and as I said, this expression has been calculated using other methods. This expression is important for what I need. I'm going to take this result, the fact that we know this result, this all-order result, and plug it into the Hamiltonian, which will allow me to sort of determine part of the Hamiltonian even at higher orders. Sure.
So A1, A2, what's the difference? Because I have A1 propagators up and A2 down, and they're parallel anyway, so it's the same as
Well,
A1 plus A2 propagators parallel, right?
A1 plus A2.
I can take one away from downstairs, put it upstairs. It's the same diagram, right?
No, I mean, for example, L1 and L1 plus epsilon is not the same as L2 L epsilon b in general because I can't think why now. Yeah, just thinking about the integral, it would seem like I could. I'd have to think about it more carefully and look at it. I can't get it quite right now.
Is that the same epsilon as in the line below, the dimension realization?
Yes, exactly. So this when I perform this bubble in dimensional regularization, I get a power of the propagator, which is the original power is minus 2 plus epsilon, because I'm working in D is 4 minus 2 epsilon. Okay. So that's sort of the one magnon dispersion relation. To go to more impurities, I need to describe the interactions, and this is where it works out very nicely to pass to sort of the S matrix description. So I describe the interactions of multiple magnons by an S matrix. So here I just have two impurities kind of moving past each other. I've pulled out all the vacuum Z's, right? So I'm going to sort of drop them, but it's worthwhile remembering that they're there in the background. Okay, so assuming all loop integrability, so as I said, this is an assumption, but the spectrum of long operators can just be found from the asymptotic beta equations. Right? So here are the beta equations for the SU2 sector, the sort of conjectured exact beta equations. They depend on these spectral parameters, x plus and x minus, which are related to the magnon momenta by this sort of formula here, x plus over x minus just gives you e to the I p. So this is sort of the normal e to the I p, L that you see on the left-hand side of the beta equations. And then you have some matrix element. And then this key piece here is the so-called dressing phase. This dressing phase is, in some sense, the thing that I'm going to be most interested in checking. That weak coupling, it only starts to contribute at 4 loops, and so for the longest time, as Thomas mentioned, people kind of neglected its presence in the spin chain. But it's very important to include it, and its general structure has been described by Nick Bysert and Thomas in a paper a while ago, and then of course others. And it has this nice bilinear and conserved charges sort of expression. These Q's are sort of the higher conserved charges that you get in integrable models. And then there's these coefficients. And actually determining these coefficients is the real test, what these actually are. It's constrained by crossing symmetry, but as was pointed out by Yannick. Here I'm talking about the spin chain, but of course, given that there's this all loop problem, there is an underlying sort of sigma model, and while the sigma model is not Lorentz invariant, it does have a sort of Lorentz invariance. In any case, the normal crossing relation can be generalized, and this dressing phase is constrained by that equation. It's universal to all the sectors. This is another thing. So it doesn't matter whether I'm looking at the SU2 sector or whether I'm looking at other fermions or whatnot. It should always be the same. So if I test it here, I test it for all sectors. And then, as I said, it's trivial to weak coupling to 3 loops, but it's sort of immediately, even at tree level, it's obvious that you need a dressing phase at strong coupling. So this is the conjecture, the BHL-BES conjecture. You start from strong coupling. This is the strong coupling expansion of these coefficients C, as I said. You can see they involve these zeta functions, and they're reasonably whatever, well, I don't know, depending on, given how difficult the problem is, this is a simple expression. But it's an asymptotic expansion, which does have an essential singularity. So this expansion doesn't really actually define the function. As I can see here, it's a strong coupling expansion. G, sorry, I think I actually did say before, but G is just related to the square root of the Ethoff coupling. Okay, so as I said, it matches the known tree level and next to leading order string Roche calculations. It solves the crossing equation. The crossing equation, of course, doesn't actually determine this dressing phase. It doesn't determine it uniquely. It only determines it up to homogeneous solutions. In normal integral models, you would use things like the relativistic invariance or knowledge of the bound states or large n expansions or whatnot to kind of fix it. Here, because the problem is a little bit more complicated, because relativistic invariance doesn't really work, it hasn't been, you can't completely pin it down. So that's why it's still worth checking. Okay, as I said, this expansion, of course, doesn't actually even define the function, so we would like to know what is sort of a convergent expansion for it. Also, we would like to know what is the weak coupling expansion so that we can match with gauge theory calculations. And so BES just conjectured this relation. You take the strong coupling expansion, you analytically continue in N, and this gives you a weak coupling expansion for the same expression when plugged back in. There's no real way to sort of prove this. It actually shows up in sort of a frightening number of different areas in physics. It's similar to sort of the relationship that you get in matrix models when you go from weak to strong coupling in it also shows up in Wilson loops. There you do have exact expressions for the Wilson loop in terms of the Ethoff coupling, and you get the sort of the correlation functions, the expectation value satisfy similar relations. So it's okay. So it's not. I mean, I'm not saying this. It's just it is surprising that it shows up in so many different in different areas. In any case, once we have this, we can sort of take this as our conjecture.
You said G was the square root of the Ethoff coupling?
Yes.
I thought they always get even powers of G.
Right. Indeed, that's a good point. So actually what will happen is that if you actually then look at the expressions that you get after performing this analytic continuation, you only do get even powers in G. And so you do get a regular power expansion in integer powers of the Ethoff coupling. Yep. That was sort of one of the first sort of checks that they looked at, and sort of, I think, okay. Well, yeah, as I said. Okay, so it is actually a series in integer powers of lambda, but that depends on the explicit expression for these C's after you do the continuation. In the SL2 sector, it matches with this very complicated calculation of the for-loop cusp anomalous dimension extracted from the gluon scattering amplitude done by Byrne et al., and then followed up by Kachazo and Spradl and Volovich. And this calculation is a real, as everyone says, tour de force. It's calculated using these generalized unitarity methods. And so this gives us kind of it's only in some sense one number, but it gives us sort of a reasonable confidence that that's one rigorous test that it's passed. The phase does start to contribute to anomalous dimensions of long operators at 4 loops through a term, which is C23. So this is sort of, here it enters with G3, but the actual contribution to the anomalous dimension will end up being at 4 loops. This would be what do you call lambda to the fourth. This parameter here, I'm going to pull off the G dependence when we actually go to the spin chain Hamiltonian. And so it's this 4 to the zeta 3 that's the actual coefficient that we want to see showing up in the actual spin chain calculation in the Hamiltonian. Okay. So as I said, while the existing evidence is quite strong, we would like to just actually see, and as I said, this for gluon for loop calculation is a real test. It would be nice just to see it sort of directly, just as sort of most transparently as possible. And so that's what we're going to try and do. We'll just try and calculate can we see this 4 to the zeta 3 actually appear in anomalous dimensions, matrix elements or anomalous dimensions. So as I said, we'll use the symmetries. We will restrict to an SU2 sector, which means that the Hamiltonian has to have this residual SU2 sector. If you exchange one type of scalar for the other, well, it has to be symmetric. We'll use known results. So we'll use the fact that the vacuum is protected and so it doesn't get corrected. We'll use the one magnon result. We'll use just constraints from Feynman diagrammatics that tells you that certain types of interactions that you might sort of generically write down in a spin chain of say, various lengths or whatnot, just can't arise. But we won't use integrability, right? So we'll just write down the most general Hamiltonian that we can that follows from these inputs, but not integrability. And then what we'll try and do is we'll try and sort of find which interactions correspond to these maximally shuffling interactions. So these are the ones that we're going to be actually able to evaluate because we won't have to worry about gluons and fermions and all the sorts of things that make doing normal Feynman diagrams a complete nightmare. And so then these ones can be explicitly calculated. So this is the approach. There are previous results that were useful in going along. The spin chain Hamiltonian, which corresponded to the AFS matrix, so corresponded to putting in a dressing phase conjectured based on tree-level S matrix calculations, has been constructed. This also had BMN scaling and assumes something called integrability, which is probably related to integrability. I should have tried to be funny. It's just dreadful. Okay, so then there's a 5-loop spin chain Hamiltonian, which also assumed integrability, Feynman diagrammatics, and known results, and also assumed a smooth continuum limit. And this actually, we'll see that the Hamiltonian that we get will actually be of sort of the same class as this Hamiltonian. So that the Hamiltonian that we find, just using sort of known results, will be the same as an integrable Hamiltonian. And so basically what I'm saying is that at 4 loops, the symmetries and the known results sort of guarantee that your Hamiltonian has to be of the integrable sort.
So how do you know that the non-maximally shuffling interactions don't contribute? Is that just a conjecture?
No, so what I will do is I will calculate specific interactions that only get contributions from the maximally shuffling ones. I'll show you the example, but you can see that there are certain matrix elements that only get contributions from these maximally shuffling interactions. And this, in some sense, you're just very lucky, but that you can pick these out. So the notation to write the Hamiltonian, I'll show it in the next slide, it's kind of a mess, but we use these sort of brackets which basically just correspond to products of permutation operators. Right? So M, L, L mean that I take the n's and the n, well, I take the I take the n and the n plus 1 site and I permute them, the m and the n plus 1 site, permute them, and so on. Also, you can always make a similarity transformation of the Hamiltonian which doesn't change the spectrum, and so there's an ambiguity. I mean, of course, the anomalous dimensions are physical observables, they're fixed, they're unique, but in the Hamiltonian we'll see that there are sort of parameters that are not actually fixed. They're just, as I said, they're related to similarity transformations. Okay, so this is our Hamiltonian to 4 loops, fixed by those constraints, as I mentioned. It has one important degree of freedom, this beta 2 to the 3, which corresponds to that factor in the dressing phase. And as you can see, it arises in different places throughout the Hamiltonian. The interactions in blue are these so-called maximally shuffling interactions. And then there are these other parameters, epsilon, which appear in various different places, and they correspond to these similarity transformations. So as you can see, this interesting parameter, beta, appears in a couple of places, like for example here, in the interaction, which is just a single permutation. This interaction gets contributions from all sorts of Feynman diagrams, and gluons and fermions, and would be a nightmare to compute. Fortunately, it also appears here in this maximally shuffling interaction. So this maximally shuffling interaction we'll be able to evaluate only using scalar diagrams. It does have one sort of parameter, epsilon, that we also need to remove so that we can determine this uniquely. But by determining the other maximally shuffling interactions, we can fix these parameters in the case at hand. One thing I should say that is important, the reason that this Hamiltonian is of the integrable sort is that there's actually no genuine 3-body kind of interactions in this. At 4 loops, you have 5 lattice sites interactions. So you sort of could imagine having sort of 3, magnons, and which would interact. But by this SU2 symmetry, this corresponds to 2 magnons and 3 vacuum sites. And so there's all the 3 interactions are related to 2-body interactions. And in that sense, this is why there's no real 3-particle genuine scattering, which would actually start at 5 loops and can involve 6 lattice sites. Okay. Yes. So in that sense, the symmetry here puts very strong constraints on the Hamiltonian and essentially fixes it to be of this integrable sort. So this 4-loop Hamiltonian has to be an integrable Hamiltonian. The important parameter, beta, as I said, okay, so it does occur in the coefficient of this maximally shuffling interaction. And then it's also important that the maximally shuffling interactions can be identified by specific matrix elements. So for example, if I consider the 4-loop Hamiltonian acting on such a 4-particle or a 4 site, and I look at the element that takes me to this sort of combination, the only interaction that does this is this 2, 1, 3, 2. So if I evaluate this C, I evaluate the coefficient of this interaction. So therefore, to evaluate this coefficient, I only need to evaluate this particular diagram, right? So I don't have no gluons, no fermions. A priori, of course, I could. I mean, you have to think through exactly, you have to think through the combinatorics, and the Dirac matrices essentially mean that you can't have any fermion loops and you can't have any gluons. Gluons won't exchange flavor, so the interaction won't cause you to permute, and so on. But after just sitting down and sort of trying to draw the diagrams for a while, it becomes becomes quite clear that the only types of interactions you can have are scalar vertices. Okay. So these, of course, are massless particles, so this IR divergent. You have to have a regulator, so we put in sort of a momentum, an external momentum. You just need 1 for this diagram. For some of the other diagrams, I think you need 2, but that's the most. It's all done in dimensional regularization. And importantly, we want to determine an overall divergence. If you actually calculate sort of this diagram, you'll see that it has higher poles, right? It has poles to epsilon to the 4th, and these just correspond to divergences in sub-diagrams. So you need to, remove introduce counterterms for all of the sub-divergences and remove those to get the overall degree of divergence, and this is the matrix element. There's actually a very nice iterative method that was described by Sir Christensen and Staudacher, again, back when they were calculating these things. And this gives a very nice combinatorial kind of determined method for pulling off the diagrams. You can actually, of course, see that it works in the end because if your prescription is right, you should just end up with a single 1 over epsilon pole. And I'll quickly run through what that actually looks like in one case. Okay, so the actual diagrammatic calculation, I'm going to use this as an example. This diagram, this is actually the one that, this This is the diagram that has the beta parameter in its coefficient. We want to reduce the diagrams, a sort of standard method. I won't try to spend too long. You just evaluate all the bubbles. You use the triangle rule to sort of take your diagrams and reduce them to sort of a standard class. And then you sort of look through the literature and the programs that you have at hand to evaluate this standard class of diagrams. So just to give one kind of example of what we do, well, as I said, we use the triangle rule. This may be familiar. It wasn't to me when I was doing this, so I'll just quickly run through it. If you have a Feynman diagram like this, which involves a triangle with powers of propagators A1, A2, A3, A4, A5, this Feynman diagram can be related to others by this triangle rule. Such that the original one is related to this linear combination, where these sort of symbols mean I take this diagram and I either increase the propagator, so say 2, I increase the propagator 2 by 1 power, or I increase the propagator power of 5, I reduce it by 1. And so this actually allows you to simplify diagrams, because if you have integer powers on these propagators, it shrinks the propagator and you get sort of simple diagrams. So just as a very quick example, if we take the diagram that we're interested in, down here we have a bubble, so we can just evaluate this bubble, so it's proportional to this diagram times some bubble. Then we apply the triangle rule to, for example, to this regime here. So this is my triangle, here's my external legs. The triangle rule takes this, and it gives me linear combinations. Here you can see I've, sorry, what I do is I kind of shrink this leg here, so then I just have this line and this line, which is a bubble, which I can then evaluate, and I get a simple two-loop diagram like this. So what I have to do, of course, I have to shrink the leg 1, so I get some diagram like this, and there's actually 2 others which cancel. Anyway, then you just keep doing this over and over and over, and finally you'll get some sort of reasonably simple combination like this, where this T corresponds to this type of master diagram. So this is actually a reasonably common diagram that you see in the literature. Here we need to evaluate it for sort of arbitrary powers of propagators, which gets very tedious. There's techniques. You kind of use Mellon-Barnes parameterization. Again, you can use the triangle rule. The Mellon-Barnes parameterization allows you to sort of perform the Feynman parameter integrals in sort of a straightforward fashion. And then the remaining integrals just end up being contour integrals, which you can evaluate using the residue theorem. Or, even better, you can use sort of automated programs which allow you to do these things. This MB program is very useful for evaluating these Mellon-Barnes integrals by Chacon. So in this case, we can evaluate the final this diagram, this maximally shuffling, which I've now called I4A, and you get some sort of expression. Here I have pulled out sort of 4 bubble diagrams, and importantly, this then will have 4 inverse powers of epsilon. So we need to subtract off the higher epsilon terms, right? So we get down to the leading pole. And of course, here we can see this is what's going to happen, right? Here I'm going to have, this is going to end up, after I subtract off the higher divergences, I'm going to get this zeta 3. The coefficients will clear up. The rules for doing the subtraction, as I said, you can derive it by just considering sort of the proper normal ordering of vertices of connected diagrams, as was done in the appendix. There's sort of a simple kind of rule for doing these things. It's essentially playing Tetris. So you take your diagram, so here's my for-loop diagram, and I want to take all the different possible partitions of this diagram. But I have to take them in a certain way, right? So I have to take some partition with a box, and then I have to drop another one on it. So I'm only allowed to get the partitions that I can form by playing Tetris. Okay, it's kind of cute. It actually becomes fun in some way, and it's certainly better than sort of normal ordering various things. The coefficients are determined, if I end up with 2 kind of boxes at the very top, I throw that diagram away. The coefficient, the overall coefficient, is given by the loop order of the highest box. So here, of course, you take, this is 4 loops, I include all of them. Here, I'm taking the top 2 sort of vertices. This gives me kind of a 2 loop here. And the bottom 2, this gives me 2 loops. Similarly, here I have 2 loops, 2 loops. And down here, I've taken all of the vertices. I've partitioned the diagram completely. Okay, my boxes are off by a little, but anyway, this box is meant to lie on top of this top vertex, and so I get coefficient 1. The sign is determined by the number of partitions. So if I have 4 partitions, I get a minus sign. No, that's not right. Something's wrong. Oh, sorry, 1 partition, minus sign. Right, 2 plus sign, so on. Can't count. Okay. Okay, so you do this, and as I said, these rules can be explicitly derived. You can then calculate what the actual coefficient of this diagram is, and the leading pole gives you -4 plus 4 zeta 3. You can evaluate all of the other maximally shuffling diagrams. This allows you to determine these epsilon parameters, and then finally you can extract what this value is. And indeed, you get 4 to the zeta 3. Okay, so that's, as I said, a sort of a long calculation. You'd like to know, okay, so given that we've done that, and it matches, and of course that's great, and I mean that was the point, and that's, I think, a very good check. What can we do? You'd like to, okay, well, can you go to higher orders? Of course, that would be nice. I mean, it gets tricky. The Hamiltonian starts to not be so strongly fixed by the symmetries. You end up with more degrees of freedom, more like undetermined parameters. Of course, you have more maximally shuffling terms, so you explicitly, in principle, you of course could do it. The problem really is actually just determining the Hamiltonian. You can at least show that the sort of higher zeta functions that you do expect in the dressing phase will appear, so I can sort of evaluate some of these interactions. And here you can see it's 6 loops, I'll get zeta to the 5. It's 8 loops, I'll get zeta to the 7. Of course, these don't, I haven't determined what these sort of similarity transformations are. I haven't determined what the right combinations are, so I can't fix a term in the dressing phase. It would be nice if there was a simple iterative prescription for sort of determining them, or, kind of in a sort of, straightforward way. It's not clear that that's actually possible, and that's sort of disappointing. And the second thing that's also sort of disappointing is that you would really like to go to sort of short operators. All of this I've been talking about long operators. Like you'd like to do, Kenishi or something like this, and for loop Kenishi, but you can't. In this case, the idea of maximally shuffling, when you work on short operators, it breaks down, and those interactions will end up getting contributions from all of these other Feynman diagrams, and so you end up sort of having to deal with the full problem all over again. Perhaps more, powerful perturbative methods. Of course, these generalized Unitarian methods are extraordinarily powerful, and maybe it's possible to use those, and maybe the way to go. Okay, so far we've only considered just the SU2 sector. We'd like to, of course, describe the full theory. As sort of an intermediate step, it's useful to kind of consider the so-called SU2-3 sector. The fields in this sector are 3 scalars and 2 fermions. The spin chain, of course, is now dynamic. Because in this sector, if I look at the action of supersymmetry generators, it can, the supersymmetry involves commutators of 2 fields like this, so you can add lattice sites. So the number of sites in my spin chain can change. Again, I choose as my vacuum this protected state. The residual symmetry, the symmetry that preserves the number of impurities, is just SU2/2. But there's 2 important modifications. There's additional central charges, K and P, which have to be added in. Well, they have to be added in so that the one motivation is that the one mag non-dispersion relation has to depend on a continuous parameter. And if you look at the representation theory of SU2/2, there's no appropriate choice. So by adding in these additional central charges, you can go to this. From the string theory point of view, these central charges make to me anyway, they have a very natural interpretation. They just arise from the fact that your algebra is only, when you're looking at the algebra of a constrained system, the algebra is only closed up to constraints. And indeed, in Lycombe gauge, which is the natural dual picture to this, you'll see that if you look at the algebra of 2 supersymmetry generators, it only closes up to the level matching condition. And so that's what happens. The level matching, these sort of operators correspond to the level matching condition or to the world sheet momentum. And they have sort of a reasonable interpretation in terms of the momenta of the spin chain momenta. The supersymmetries have a non-trivial coproduct. They don't satisfy a normal Leibniz rule. And this also has its origin in the fact that they kind of add in a vacuum state. And I'll try and explain just a little bit in the next slide. Importantly, the global symmetries are enough to sort of uniquely determine the S matrix up to an overall phase. So not just in the SU2 sector, but I can determine all the matrix elements, and they're all related to each other by the symmetries, and that's just due to the special representation theory of this algebra. So this is the symmetry algebra, the SU2/2, acting on single particle states. And this was the point that I wanted to make. If you look at the supersymmetries acting on certain states, they have these sort of operators. This Z minus means I destroy a kind of a vacuum state. Z plus means I create a vacuum state, and this gives rise to this so-called non-trivial coproduct. So if I want to take one of these vacuum states, you have to remember these operators are like sums over linear combinations. So if I remove a state, and move it to the other side of an impurity, I pick up a phase. So if I act with Q on two particle states, you'll see that it acts sort of naturally on one particle state, but when I move to the other side, it picks up a phase. I can also write this as a coproduct. This just means that Q acting on two particle states acts in a natural way. On the second state, it picks up a phase. You can actually generalize this sort of coproduct to a sort of full Hopf algebra by defining sort of the normal canonical elements that you need, such as the unit and the antipode. And this actually this should be a powerful method for studying the full problem. This sort of algebraic approach has proven very powerful in other known integrable systems. And in any case provides a sort of a general language for talking about these things. Okay, so that's the symmetries. I now want to sort of move towards the sigma model description in sort of the last half or last third of the talk. And so far we've been sort of looking at the theory from sort of the weak coupling point of view. I now want to talk to the sigma model, where we kind of study the problem with strong coupling. Here we can consider the conjectured S matrix, and we want to go beyond sort of the known one-loop results of like Hernandez-Lopez and Saitlin and many others. There are actually known recent two-loop results, recent a couple of months ago, by Weiban, Tirtsu, and Saitlin, and Weiban and Saitlin, which are relevant to calculating the two-loop cusp anomalous dimension. Our approach is different. I mean, it's just looking at a different type of part of the sigma model, different classical solution. The worldsheet sigma model in general is quite a complicated problem. Looking at the sort of gauge fixed light cone gauge, the symmetries are not manifest. You can work in it, but it really is quite a challenging problem. So it's useful to sort of study simplifying limits, and to that end, and as Thomas described yesterday, we'll consider the near flat limit described originally by Maldacena and Swanson, which results in tremendous simplifications of the action. But before I actually go on to describing the results, well, let me just say what the near flat limit is. My point I want to make is that it is a very nice simplification, but it actually does capture a lot of physics of the problem. And I'll try and have a couple slides just to say kind of that it does actually get a lot. Okay, so there's sort of three regimes of sort of interest that you consider. The so-called giant Magnon limit, where you look at the momentum of the excitations and you keep it fixed while you take the coupling strong. And in that case, the dispersion relation, you see this sort of sign dependence, right? The sign dependence comes out. In this case, we're looking at the regime where these spectral parameters x plus goes like 1 over x minus. Up here, I've sort of written in very small font the relations, just to remind you. The plane wave limit is where we take square root lambda p fixed. So we look at momentum k, which is given by this combination, and then we take lambda to be large and we take p to be small. And in that case, the dispersion relation gives you this sort of Lorentz form of square root sort of 1 plus k squared. The regime that we're going to be interested in is this sort of interpolating limit, this near flat limit, where the near flat part, while it's sort of confusing, the reason for the name is that we scale the momentum such that it goes like lambda to the fourth, or inverse lambda to the fourth. So this is the combination that we keep fixed. It's not really near the sort of, normally you think of AdS as sort of a standard flat space limit, and that's not the flat space limit that we're actually considering. We do consider the regime where the sort of momentum scale in this way, but we're only going to consider left movers. Another way of saying it is we consider the regime where the spectral parameters are close to -1, where both of them are close to -1. And then this is sort of the part that's the way, depending on this combination k, which is lambda to the fourth p. There's some constants, and this k will essentially be sort of the left moving light cone momentum, p minus on the world sheet. In this limit, the dispersion relation has sort of a leading divergent part, lambda to the fourth k, because again, we're interested in the large lambda limit. And then it has sort of a subleading part. We'll actually be interested in a combination where we subtract off this piece, rescale by lambda to the fourth, and so this will actually end up being sort of the light cone energy of our sort of excitations. So that's sort of the limit in terms of the spectral parameters, in terms of, so you could use this then to take the limit of the S matrix, and indeed we will. You can also just think of it in terms of, well, what is the actual algebra of this reduced system? Well, essentially, the actual algebra is the same. I introduce sort of new central charges, and then I rescale them. So K plus is C. C is the sort of energy in the original algebra. It's the dilatation operator in the original algebra. This and then K and P, as I said, are these additional central charges. So I form these two linear combinations, or these three linear combinations. What happens in a simple way is that K minus essentially becomes the light cone momentum of our excitations. K plus is the light cone energy of our excitations, and K2, I should say, is higher powers of the momentum. We also kind of form linear combinations of the supersymmetry generators, and indeed rescale those too. And then we find that the full algebra, this is just essentially a rewriting of the original algebra. All the scaling kind of drops out. I have the same number of charges and whatnot. It's just it's a convenient way of writing the algebra. Here are all the SU2 generators. I've just kind of combined them into sort of it's a messier formula. So this is essentially this part. The thing that does simplify quite dramatically is we still have a coproduct, a non-trivial coproduct. So for example, here's the supersymmetry generator, and indeed we see that it has a non-trivial piece. It's different than the coproduct in the full theory, but it's still non-trivial for the global charges. So there's still a non-trivial braiding in this limit. So in that sense, it's simpler, but actually it does still have a lot of sort of the non-locality doesn't wash out. Okay. So the near-flat S matrix, I said we can take the limit of the exact conjectured S matrix, and we can ask, well, what is the limit what is the near-flat limit of that S matrix? So here I've written S as sort of a dressing part and an OR matrix part, and these are the here's the notation that I use. So the different OR matrix elements are given by A, B, C, D. For example, A is just 2 bosons into 2 bosons, where I don't flip the flavors. I introduce parameters, theta, which is sort of the normal rapidity, and then I have this sort of coupling. So of course, in this limit, I can sort of scale lambda out, and so these are the sort of the 2 parameters that I have left in the S matrix after taking this limit. I have P over P prime and P times P prime. So this ends up, so these are the 2 parameters I have, and I can write the OR matrix elements in terms of these 2 parameters as so. Then they're reasonably simple. They seem certainly simpler than the full theory. I'm not sure what they're suggestive of. One thing is that if K will end up sort of looking like, well, you can consider it as sort of a momentum-dependent coupling constant. And if you do that, then these things sort of look relativistic invariant, right? They only depend on the difference of rapidities. You can actually do a little bit better. This is one thing I just want to say. You can pull out a further overall factor. So I can write the total S matrix as this e to the I delta times this extra factor, which I'm going to pull out, times, this is the full OR matrix, the full PSU2/2 squared. And then I have 2 powers of this OR matrix, and this is the OR matrix here. One thing that I want to say is that this OR matrix is sort of tree-level exact, right? It has a tree-level piece, and that's it. And yet, this is meant to be the exact OR matrix in this limit, which is a little bit confusing. But you can actually check that the OR matrix satisfies the classical Yang-Baxter equation, and it satisfies the quantum Yang-Baxter equation. So again, I mean, I don't know of anything profound about that fact. It just is the fact that the model it has a non-trivial dressing, but also it sort of simplifies quite dramatically. You can take the classical limit of the representation, right? This model has a sort of a genuine classical limit, and so I can sort of introduce classical generators, and I can then try and write down a universal classical OR matrix. This OR matrix, of course, before in the previous slide, is on a specific representation. I'd like to be able to write the OR matrix in terms of sort of generators, so that it's sort of representation independent. And following sort of work by Torelli and Moriyama and by Bicert and Spill, where they did this sort of for the classical limit of the full theory, you can just straightforwardly do exactly the same thing in this reduced limit. And you do find sort of, again, this is the point, you find something similar to what they find. You find sort of a normal, sort of what you would expect, quadratic Casimir sort of looking terms, and then you find these strange, these additional terms here at the end. Okay, so that's I just want to say that it does indeed have a kind of a classical universal R matrix. I mean, I can't prove that this is a universal matrix. This is sort of a conjecture. And it has a lot of the same algebraic structure as the full problem. I can take the limit of the dressing phase, and I'm not actually going to go through the steps, but the actual dressing phase simplifies really quite dramatically, and to 2 loops at strong coupling in the near flat limit, this is the dressing phase. So really, well, this is the dressing phase.
So what's the loop expansion parameter in terms of the parameters of the near flat space limit?
So here, the sort of I'm doing a small momentum expansion.
But in terms of kappa and theta, I mean, if you were to take the
Kappa, expanding in powers of kappa.
kappa.
Yes. Yeah. And that's what I wanted to say is that here you can see that I only get even powers of kappa. The odd powers of kappa that kind of sort of normally arise in the dressing phase, they actually cancel. They cancel in this limit against an other overall part of the sort of another overall constant piece.
You've got all powers of kappa in that expression, right?
Hmm?
You've got a tangent squared of kappa, so that has a. I'm just trying to work out if you were to get the 3-loop contribution and compare it to this in the near flat space limit, what would differ? I mean, it would be suppressed by an extra power of kappa, or
Yeah, an extra power of kappa. You'll see that the 3-loop piece would have higher powers of momentum. So kappa is small, right? So yeah.
But you're keeping all powers of kappa in that expression.
You're okay. Yes.
quite,
Yeah. Okay. So I've cheated a little. You're right. I mean, really, this expression. So I've taken 1 plus, and I've written it as an exponential. But you're right. It's only valid to sort of 2 powers of kappa.
Okay.
Yes. You're right. You're right. This is a little confusing. Yes. But it's only valid to 2 powers of kappa. So in order to actually match with the perturbative calculation, I have to expand this. Yes. Okay, so the Lagrangian. This is Lagrangian, as Thomas discussed a little bit. I won't spend too much time on it. Sort of the quadratic piece is just the plane wave, gauge fixed, Lycombe gauge fixed action. So I have sort of relativistic invariant, and then I have these interactions, and they're maybe not the prettiest thing, but they're a lot better than the full problem. Sort of the bosonic interactions you can see here are actually reasonably simple. Importantly, they only involved partial D minus, right? The left-moving derivatives. And they also only involve a particular combination of the fermions, these sort of left-moving fermions. You can calculate this by gauge fixing the Lagrangian, doing normal Lycombe gauge fixing, and then taking the near flat limit, and you have to make a field redefinition, and you'll get this action. Importantly, you can gauge fix in sort of a range of different Lycombe gauges, right? It's a sort of genuine Lycombe gauge and the so-called uniform gauge and so on. All of that doesn't matter in this limit. The sort of the gauge dependence, the Lycombe, the sort of the interpolating Lycombe gauges. I just meant to say is that a lot of the sort of the the full problem, the sort of the range of complexity, or a lot of the sort of superficial complexity that arises in the full problem doesn't arise in this problem, and that's the point I wanted to make.
So you don't have a coupling constant in the action. The coupling constant only appears when you expand in momentum.
See, this is the thing. So really, there's no coupling constant. In the limit, it drops out, right? Because I rescale the momenta by the coupling constant, and then I only keep the pairs with this combination drops out. Now, what I can do, of course, is I can actually rescale the fields and put in and indeed that's what I will do, and that will sort of look like my coupling constant expansion. But really, I'm expanding in powers of momentum. As I said, okay, so this is this part. The action is supposed to be exact in this limit, right? And this is then a little tricky. So before, what I did was I took the full quantum S matrix and I take a near flat limit of it. Fine. Here, what I'm going to do is I take a classical action, I take a near flat limit of it, and then I calculate quantum corrections. These two things are not guaranteed to be the same at all. Right? Absolutely. Okay. So the thing is, if it doesn't work, I can't tell you that I've disproved anything. The fact that it does work means that at least it seems like a good consistency check. And another way of thinking of it is this: is that I can do loop calculations like the one loop calculation, and I can see that there are no contributions from the sort of states that are the modes that I've neglected. And then I get I gain confidence that the higher pieces are going to. So this is a little tricky. The point is this: is that yes, it doesn't form like a rigorous proof or disproof of the conjecture. I think what it does is that it checks things like the symmetries. It checks things that and it gives you confidence that the actual expansion is right when it agrees. Okay. So, but that is an important point to make.
When the Lagrangians in this form, is there a coefficient in front of the action that you could fill a cup in?
No, I mean
Just
there
one?
would be it's just one. Yeah. So you're doing a momentum expansion.
So if you find any divergences, you're in trouble, right? Because you've got no way sort of.
Yeah. Of course, actually, as it works out, this model has no divergences. The one where we don't make this funny limit does have divergences. That I don't know how to explain. Yeah. Actually, here it's also a little bit nice in that there is actually the worldsheet supersymmetry. It's not obviously manifest here, but you can actually see that this theory does have at least a 0, 2 worldsheet supersymmetry, as you would. Okay, so that's kind of nice.
Why would you?
Well,
you expect that? We're in
okay.
Schwarz formalism.
Yeah, but the Green-Schwarz formalism in light cone gauge, say in flat space, you can actually show that there is a worldsheet supersymmetry.
I thought that was just because of flat space.
Well, okay. I mean, talking to people, it seems that people do expect that there should be some maybe relationship between the different formulations, even in curved space. Now, of course, you're right. It's only been, well, at least it's been shown in, say, flat space PP wave, right? Here, you can see it, at least half of it. So that's interesting, right? Yeah. That does, I mean, that's, as to whether you're expected or surprised by it, well, okay. But I think other people, yes. Okay, so the model does have, I'm going to run a bit long. So the model does have Magnon solutions. I just wanted to, this perhaps is not, it is an interpolating limit, but sometimes people maybe forget. This was pointed out by model saints once. Here I've taken slightly a different approach. This is actually, these are Magnon solutions of the action that I presented, not some sort of limit of the other Magnons. And it's straightforward, right? You can choose an ansatz. Here, of course, it's sort of a light cone. I've chosen sigma plus to be my light cone time. I get sort of the normal method, and I can calculate what the energy, what the light cone momentum and the worldsheet energy are for these Magnons, and indeed I get sort of the expressions that I would expect. So there's no sign here, right? But this is sort of like expanding the sign in this near flat limit. So this is sort of the classical part that I would get after expanding the sign. Okay, so this is that's all I just want to say. And indeed you can find the sort of higher charge Magnons too. Okay, the string. Okay, so now what I want to do in just this last bit very quickly is we actually go ahead and calculate the S matrix, just perturbatively about a plane wave background. So we look at excitations, fluctuations about the quadratic plane wave and calculate their S matrix, and then match that to the BHL BES conjecture. Okay, we can do it for the full theory, right? So it's including all the bosons and all the fermions and whatnot. Thomas talked a little bit about this, and so he explained, what the different fields are. So here we have our bosons, here we have our fermions. We've used SU2 squared indices. And as we would expect to, and as I said, we do introduce a kind of rescale of the field, so we get a coupling parameter, and we use this sort of to count our loop orders. The one loop calculation was done by Close and Zarembo. Just quickly, as an example, we can consider the matrix element A, where we take two bosons and we scatter them into two bosons. The tree level, of course, you just read off the vertices. This is the tree level S matrix. And at one loop, you just have the three bubble diagrams. You can just sum them up. This is the STU channel. Here I have, Here I get these momentum integrals. I00 in the U channel, and I can just analytically continue to get the S channel. The point that you made, okay, and indeed this is the actual answer that I get, which indeed agrees with the one loop expansion of the near flat space limit of BHL. By naive power counting, you might have expected divergences. So there's two reasons that these divergences don't arise. One, of course, the free theory does have Lorentz invariance. So sort of if you end up, and all the interactions involve powers of k minus, right? That shouldn't, oh, I'm sorry, I missed notation. I mean p minus. P minus the light cone, left moving light cone momentum. So they all depend on, all the vertices only depend on that. The propagators of the fermions have extra powers of p minus in them. The bosonic vertices have derivatives of, and so on. So you end up with integrals of this sort, and just by sort of doing the angular integration first, you can just show that these are 0. And then there's further cancellations sort of due to the symmetries of the problem, sort of the fact that you get a minus sign going from the sphere to the AdS space, and the bosons and the fermions, and so indeed all the remaining divergences cancel. This is just to say that indeed the divergences do cancel, the power-like and the logarithmic divergences. The two-loop propagator. So that's the one-loop problem, and this was done by Thomas, and so I'll just quickly go through the two-loop issue. The two-loop propagator is actually interesting in its own right. You get this sunset diagram. You get 4 powers of the momentum. Here, it's got, square root lambda squared. So this is the two-loop piece. And you end up having to evaluate just this momentum integral. On shell, it contributes 1 over 64 times. I've introduced a mass here because the mass is just, well, 1 in the notations I was using before. And I can just read off the mass shift and the wave function renormalization from the correction to the propagator. The important thing is that here we're considering time evolution in the sigma plus direction. I didn't explain the actual mode expansion, but it's true. And so that the appropriate energy is 2 times p plus. So if I calculate the correction to the dispersion relation, so here is this sigma, I find that I indeed get this two-loop correction involving 3 powers of the light cone momentum. So using the normal relation for the dispersion relation, I find this square root formula. And so here, this is the piece that I just wanted to point out. Here's the sort of free part, and here's the two-loop piece. And this is sort of the expansion of the sine function, right? So you see, and this is what you would expect, that the quantum correction in this limit, that you expect to be able to generate this sine function, these higher powers of p, right? So the full answer looks like something like square root 1 plus sine squared p. You take the near flat limit, and then at 2 loops, this is the piece. So that's quite nice. Of course, you can also see how the sort of the non-Lorentz invariance enters. I mean, the interactions are non-Lorentz invariance, so it's not surprising. But of course, you expect the dispersion relation to also take such corrections. Okay. So then we can go to the two-loop S matrix. At this point, because we now have corrections to the dispersion relation, we have to calculate the corrections to the sort of Jacobian identity that we get from these delta functions that enter into any sort of S matrix calculation. So you have to do the normal derivatives, okay? There's wave function renormalization, as I said, from calculating the corrections to the propagator. And then we just go ahead and calculate the two-loop amplitude. So the full sort of S matrix is given by this formula. And then the relevant diagrams, here I've just drawn the S channel, are these double bubbles and these so-called wine glass diagrams. Okay. All right, so these then are sort of the horrible formulas that sort of arise out of these things. So here, again, is just sort of one matrix element. It's the sort of bosonic forward scattering, and you get this contribution from the bubbles, the wine glass, the S and U wine glass, and the T wine glass. It's not immediately clear to me what's sort of what you can actually see in these formula. One thing is that they're all proportional to the tree level piece, which is sort of interesting. They have these double logs in them, which are worrying, and you want them to cancel, and indeed they will. So when you combine all of these things, they combine nicely to give you a somewhat simpler answer. And this is the sort of the final answer at 2 loops, the two-loop contribution to the matrix element A. Here, not written in terms of rapidities, but rather in terms of momenta. And you can, as I said, the double logarithms cancel, which is nice, so this actually will match. There's no double poles. That's not surprising. I mean, we're not in the giant Magnon limit. As I said, we're expanding about the sort of plane wave vacuum. It agrees with the near flat space expansion of BHL. And indeed, you can go ahead and calculate all of the remaining matrix elements, which tests whatever symmetries. I mean, sort of indirectly tests that all of the symmetries are present, and indeed they are. Okay. So I'm out of time anyway, so I'll just quickly run through. As I said, we the main point, the talk was to present perturbative calculations to test this very interesting BHL-BES conjecture using both weak coupling and strong coupling. Okay, so given that, it is interesting about, okay, what can you do? What can you do further, right? I mean, you can, of course, just go to higher orders. That's, of course, interesting. Definitely in different regimes, you might start to see new physics, and so it actually might be worthwhile doing. Okay. In the gauge theory, one of the most pressing thing, of course, is to find wrapping effects. So it's not so much there to go to higher orders, but to look at finite size operators. This is a very hard problem, and I essentially don't have anything to say. At higher loops in the sigma model, maybe things are a little bit better. The sigma model is really quite simple, this near flat limit of the sigma model. It may, I mean, it's presumably integrable to all orders. Thomas showed that there's one loop quantum integrability. You can go ahead and actually construct things like, you know, higher local charges and so on. And not that this is done, but there's a sort of a reasonable procedure for doing such a thing. It may be exactly solvable. It's complicated, but it does share certain features with, you know, known exactly solvable models. Finite size effects. The model in this case, you actually have to take the decompactification limit. You can't do this theory on the cylinder. You can't satisfy level matching condition. But it may be possible to study finite size effects in some other way. Okay, but maybe that's not so promising. But exactly solvable, I think, is well, perhaps possible. And then just the last thing is that in all of this work, I think there's been, you know, tremendous progress in understanding the gauge theory. It would be nice to see if we can learn just sort of maybe general things about string theory and curved backgrounds. I mean, these are obviously very specific types, but things like finding, you know, like a world sheet supersymmetry in a curved background, how that's actually realized, even in this special case, might be very, very interesting. Okay, I'm finished. Thank you.
You said you can't consider the model on a cylinder because of level matching.
Mm-hmm.
That means you need non-level match states for.
Because you really only have left movers.
Well, so you only have left movers.
Yeah. So it doesn't. Yeah. You can sort of go through and actually calculate the level matching condition. In this limit, it ends up being the integral over the world sheet of a real quantity squared.
Question: if you put in the Lorenz-Malus-Zenon background to get around the level matching.
Sorry, say that again?
In the Lorenz-Malus-Zenon background, you get around the level matching because there's some
Twisting on the boundary conditions.
So you might be able to find these, right, there's only left movers.
That's a good point, yeah. So absolutely. Taking the near flat limit of sort of more general models, people have looked at this, at least just for the bosonic part. It's not clear to me how much will wash out, right? I mean, some of these effects may end up washing out. Though, and in particular, I don't know what happens to the boundary conditions. But that's very possible that might get you around that.
Oh well, that's thanks for the